Hey everyone, welcome into today's lecture on arc length. So in this lecture, I'm going to set this up a little bit differently than the book. You should still read through your book and see how they set it up. The book starts with a function, a function of x, so that's totally fine. But what I'm going to start with is just a curve. So let's suppose that we have a curve, but I mean the way I drew it here, it's a function. But here's a curve, and this curve maybe implicitly is given by some equation, okay? I'm not too worried about this, but this curve has some kind of equation. And what I would like to do is say start here at x equals a and move over to here, say x equals b. I would like to try to find a way to describe the length of this curved segment right here. And so at this point, when x is, the way I set this up is exactly the same as the book so far, because I have chopped this curve into a finite interval in the x direction. But the idea is the same in the y direction, right? So we could have chopped this up in the y direction, and now notice that that's not a function, right? It's not a function in the y direction. But that's okay. So the idea here is going to be, and I'll let you read the book to get all the details, but the idea is going to be the same as you would probably guess, which is we are going to take our interval, let's just do it in the x direction because that's what we're used to, and then remember that you could do all this in the y direction as long as you're very careful. But in the x direction, let's take our interval and chop it up into a partition. So our x naught is always equal to a, and then the x's count up. This is definition of a partition from an integral, right, up to xn. And so our usual partition rules are that these have to increase. And up on the curve, we have corresponding points for these partitions, right, corresponding partition points. And the way that we're going to do this, we want to approximate the length of this curved segment. The way we're going to do it is just by drawing straight line segments. All right, so we have straight line segments. And now let's zoom in on one of them. Again, I don't want to spend too much time just doing exactly what the book has done, but it's useful to at least remember what we've got here. So we zoom in on, say, this segment, and I've changed the slope a little bit, but let's just pretend that that's the same slope. So it's the exact same picture, but zoomed in. And as we go, we can kind of approximate, or we can draw a right triangle here to represent what we've got, right? So there's a little right triangle with changes in the vertical and horizontal direction. Now again, we're probably going to think of this as a function, right? In most cases, we're going to think of this as a function in one way or the other. But in general, we don't have to, because this tiny change right here, this change, this is our dx, right? And then this change right here is our dy. And what we want to do is try to compute the change of the hypotenuse. So one of our conventions is that we're going to let the letter s represent the arc length of our curve, all right? Which means that this horizontal, or this hypotenuse of our triangle, this line segment right here that connects these 2 points, this is the approximation of the arc itself, and the arc length is going to be the length of this, right? The approximate arc length is going to be the length of this. And so we'll call this green segment right here ds, and this ds must obey the Pythagorean theorem, right? So we've got a right triangle, we've got a small change in x, a small change in y, and then we can just build our differential ds by the Pythagorean theorem, and this must be dx squared plus dy squared, square root the whole thing, right? So what we can do then is we can write down that the arc length of this curved segment C from the point AC, that's a lowercase c, right, to the point BD, this is given by, so first of all, approximately what is it? Well, it's the sum of all the lengths of these segments, which I've called ds, right? So we add up the segments ds. So this will be the sum as I goes from 1 to n. By the way, we can call this like dsi at that point, right? So once we index these, we have a little triangle for each I. And so this will be the sum of the dsi. But we want to get the exact value, so you can probably guess exactly what we're going to do, right? We're going to say, all right, we'll call this s. We're going to take the limit as n approaches infinity. And then provided this limit exists, then this is just equal to the integral. Either, there's two different ways to write this, okay? So it's either the integral from a to b of ds as a function of x, or it's the integral from c to d as ds of a function as a function of y. All right, and as always, we have to say provided the limit. Anytime that we define something by a limit, right, we have to say provided the limit exists. All right, and so that's going to be our arc length. So this idea right here, again, this is all in the book. They talk about it in a slightly different way, but it's all the same. And now what we want to do is compute with this. So we're going to need to be able to compute with our ds, and this is where the idea from the book kind of comes in. So let's do some examples here. So we'll just call this a general setup. The main idea here is that to compute the arc length, we have to integrate up the arc length differential. I mean, that should be not too crazy of a thing to say, right? So the big question then becomes, how do we integrate up something that looks like this? And so that right there is the key. You have to know what the arc length differential is if you're going to use it in these formulas, right? So let's do some examples, like I said, to see exactly how this works. So let's start with a function, f of x, or a curve that's given by a function, f of x equals 1 over x, on the interval from 1 to 2. All right? And so let's sketch this curve first of all, and then we can talk about exactly how we're going to approach this. So first of all, this curve is a hyperbola, right? Y equals 1 over x. And we know that our interval that we're asked about right now is the interval from 1 to 2. So our A and our B are 1 and 2 in this case. And so the curve segment is the portion of the red curve that's between these blue dots, right? So this is the idea. So this is our function y equals 1 over x. This could all be turned on its side, and honestly not that much would change. A little bit would change because we'd have to go the other direction, right? But this curve is a good candidate to do as either a function of x or a function of y. Let's do it as x because we haven't done anything yet, right? So what are we going to do? Well, let's remember our arc length differential, ds. This is always dx squared plus dy squared. This is the definition of the arc length differential, at least from a geometric point of view. Now, if we're going to treat our y as a function of x, then we can relate dy to dx, right? Because we can take the differential of this. Dy is going to be the derivative of this formula. So that's going to be negative 1 over x squared times dx, right? Times dx. And so we can get this entire differential, ds, in terms of x and dx by making this substitution. So we're going to make this one-for-one substitution here. We're going to swap out the dy from this formula for this one, right? For this formula. And look what we get. So then our ds, I'm going to write this as a function of x. So that's supposed to be like a subscript x, just to remind us that our ds is going to be a function of x. This becomes dx squared plus, this is just dy. So we have to square this whole thing, right? So this then becomes negative 1 over x squared dx, quantity squared, all still under the root. And let's see what happens, right? So now we have to distribute the square root. I'm going to do this one in all the steps, right? I'm going to write down all of the steps. Now this becomes plus 1 over x to the 4th, all right, dx squared. And then we can factor out this x squared here. So, or sorry, this dx squared. So this integrand can now become 1 plus 1 over x to the 4th and the square root. And when the dx comes out, the dx squared comes out, the square root cancels it because dx is a small positive change in x, right? And so there we go. And let's see what happens. So this is now all in terms of x, right? So the arc length then, the arc length is now given by the integral formula. So it's now given by the integral what? The arc length s is equal to the integral from 1 to 2 of this thing, right? So the square root 1 plus 1 over x to the 4th dx. Now, this is not a great integral to compute. You probably have to use some approximation methods on this. So I'm going to leave this one for you guys to compute. But you can rewrite this, multiply through by x to the 4th. Let's see what happens. So let's see if you actually do have to do as I claimed there. You can maybe do a trig sub here, but this becomes integral from 1 to 2. If you factor out this x to the 4th from the bottom, then it's going to leave you with 1 over x squared. We're on an interval where x is positive, so the square doesn't change anything, right? And then this is x to the 4th plus 1 dx. We can make this u substitution where, what are we going to get? So let u equal x squared. And so this is not going to work out too well, right? Because this will become u squared plus 1. This will be a u, but this term right here, the dx, will have a square root u involved in it, and so it won't change too much, honestly. But anyway, that's not the point of this. The point was to get the integral written down. So I'm going to let you guys compute this one. Compute this by numerical. So compute this correct to, let's say, 3 decimal places with one of our numerical or approximate integration methods. So approximate integration methods. So this is a good chance to review those. All right. So, and let's now review what we did to get this integral, because now the whole point here was to get this from an integral that was just this kind of theoretical, well, how do you get s? You integrate ds. Well, how do you integrate ds, right? You have to get it in terms of x or y or some variable that you can actually work with. And we were able to do that by switching this one to x. So notice that what we found here was that if you take this derivative, right, so if you have your graph, your curve represented as a function of x, then its differential is a function of x, right? And then that can go in and you can get the entire ds in terms of x. So before we actually do some where we're going to compute them, the next couple examples, let's write down these formulas. So these, I'll call these formulas for ds. Number one, the definition in some sense is actually ds squared plus dx equals dx squared plus dy squared. So Pythagorean theorem, that's where this comes from, right? Number two, this was that we had our ds was equal to the square root of the right-hand side, because we're talking about a geometric quantity that must be positive or at least non-negative. Arc length has to be, it's a length, right? So it's got to be non-negative. And so it's okay to take the square root. It makes sense to just take the positive answer. So there's no problem there. Now, number three, this is the one that we just worked out. So if our function, so if our curve is given by some function of x, so if y equals f of x, right, then our ds as a function of x can be written just like we did up here. What happened? Well, we have to square that derivative, right, when we pull everything out. So this term right here, if we just go back and compare, this is f prime of x quantity squared, because the differential has to get squared, right? The differential had to get squared. So this then becomes our ds as a function of x, which I'm just going to write as ds again. You can decide how clear you want to be about what variable you're using, but this is then going to become, after everything's factored out, it's 1 plus this derivative of f squared, and as a function of x, right, all times dx. All right, and this is how the book sets this all up, actually. So they start with a function in this direction. Now, the other option is, what if our function, what if we wanted to think of this as a function of y going this way, right? Now, for this one, everything's symmetric, so actually we'd get the same integral back. You can check that, actually. You can check that. But it's going to go from 1/2 to 1, right? Or it's going to go from 1 back to 1/2, down to 1/2 if you go in this order, right? So anyway, let's work this out. So if x is a function of y, so if x is equal to g of y, then our ds as a function of y, which again, it's still just ds, but it's just represented as a function of y, what's it going to be? Well, this time it's going to be 1. Everything's going to be the same, right? Except it's going to be in terms of y. So it's going to be 1 plus g prime of y squared, all under the square root, and then times dy. So these are the different formulas for our differential ds. So the main ones are these, right? And this is exactly what we're going to integrate up when we're computing the arc length of a curve. Okay, I've got 2 examples here, and then I want to briefly talk about something called an arc length function. But let's do these examples. So here's one example. This first example, I mean, this was kind of an example, but this was an example of like a motivating example of where we could draw the curve very easily and then work out what the integral would become. But you're going to compute that one, remember. So now I guess we're kind of on example 3, but I didn't number that one, so let's stick with this. So let's say our function is y equals the natural log of secant of x, And the interval that we want to compute this arc length on is from 0 to pi over 4 inclusive here. And so we want to compute, like I said, the arc length of this curve on this interval. We actually don't, as long as we know that the curve is well behaved, we don't actually need to sketch the curve, right? This is maybe one that's a little bit weird for us, but secant is defined, obviously, on this interval, and the outputs of secant are always greater than 1. And log is defined on all positive numbers, right? So no problem. So this is totally fine. And so let's use, because this one's already written, given to us as a function of y, or sorry, y as a function of x, let's use on this one our formula for ds as a function of x. So in other words, ds is going to be equal to 1 plus y prime squared all under the square root times dx. Now I've gotten very lazy with the y prime there. Right? Up here I wrote it as f prime of x, so we just need to be careful with this part. So let's work out this differential first, and then we can integrate the differential, right? So let's start. We need y prime. We know y, right? We need y prime. So y prime is going to be the derivative of natural log of x. Derivative of natural log is u prime over u, right? So the derivative of secant x is secant x times tangent x, and u, in this case, is just secant x. And those two secants are going to cancel because, again, secant's always greater than 1 on this interval. It's never 0 anywhere. But so then this just becomes tangent of x. I already squared it. Didn't mean to do that. I'm thinking ahead, right? So that's just tangent of x. And then what do? Well, then we have to square it. So I jumped the gun, right? So the next step is to square this derivative. That becomes tangent squared x. And then we can plug it into this differential, right? So then ds becomes 1 plus y prime squared dx. This is then equal to 1 plus tangent squared x dx. But 1 plus tangent squared is secant squared x dx. And again, secant on this interval that we're restricted to is always positive. So this is just secant of x dx, and that's our ds. All right, that's our arc length element, our arc length differential for this function. And so now the only thing we have to do is integrate that, right? So now we have this definite integral. So let me write it down. The arc length is then given by this, right? S is equal to the integral, in this case from 0 to pi over 4 of ds, which is integral from 0 to pi over 4 of secant x dx. This should have said ds of x, right? Just, again, these are x values. Be very careful with what these boundary things are, because if those are s, then this is simple, right? But those are not s values. Those are x values. All right, and now we go for it, right? Well, what's the antiderivative of secant x? We can use fundamental theorem here. It's the natural log of secant x plus tangent of x, and then we're going to plug in these x values, right? X equals 0 to pi over 4. And so we'll do these one at a time, right? So this is then the log of secant pi over 4 plus tangent of pi over 4 minus the natural log of secant of 0 plus tangent of 0. You should know these by heart. So secant of pi over 4 is square root 2. Tangent of pi over 4 is 1. Log on this side, secant of 0 is 1, and tangent of 0 is 0. So this ends up being, this arc length is equal to the natural log of 1 plus root 2. I'll just change that. And obviously these are positive numbers, so we don't need those bars anymore. Minus the natural log of 1, but the natural log of 1 is 0, right? And so here we have the natural log of 1 plus root 2. And that's our answer. Okay, now at this point I want to know, so that's the arc length of this curve on this interval, right? So again, secant is defined, here's how secant behaves. Let's just look at one kind of half period of secant. So secant is always wedged between these asymptotes, negative pi over 2 and pi over 2, and in between its graph goes through 1, and it's like a very tight asymptotic kind of parabola looking, but it's absolutely not, right? Because it's squeezed between there. So it looks like this. And what we just computed was the arc length of the curve, this is not the curve, by the way, then you have to take the log of these values, right? But the inside function here determines the domain the most, because what we did was we went from 0 to pi over 4, right? So these are the inputs that we use for our log function. So these then get input to the natural log of u, you might say, right? And that goes from 1 and it gets bigger, right? That's the idea. Well, log is defined from 1 to infinity, certainly, right? So actually we could ask ourselves, what if we took this point and we tried to slide it out, right, out here? Well, what would that cause us to have to do? Down below, our x value would have to approach pi over 2, right? So actually, let's ask ourselves this. And by the way, what if we could even ask in the other direction as well, right? What if we took that and we pushed it back toward this way? It can go all the way over to negative pi over 2, open. That's supposed to be an open circle, right? So actually, this function, so that's kind of the end of the example, but I'm going to say more, right? So this function, y equals the natural log of secant of x, is defined, and like well-defined, continuous. So let's say that, and continuous on the interval from negative pi over 2 to pi over 2, right? Open. This is for the x's, right? That's the domain of the x's. So actually, what we just did when we took the arc length from 0 to pi over 4, that was only a small subinterval, right? It might be the case that we want to move that point around, just like I drew in this picture, right? Move the endpoint around. So let's say, for the sake of this argument, that we're going to fix the starting point and we're going to move the endpoint around, and we want to know how long is the curve, right? How long is the curve? And so what we can do is we can build an arc length function. So the arc length function, which we'll say is s as a function of s of x. In this case, you could do this in terms of y as well, right? If your function is conducive to that, but in this case, it's maybe it is, but it's not given to us that way, right? So in terms of x, and it's going to be then equal to the integral from x naught to x of this function f of u du. It's not true. That's not what I meant. I'm sorry. If we're gonna integrate, so this function s of x is then going to be in terms of our arc length element, right? ds of u. So these become u values. So this is a little weird, right? So let me write it out a little bit clearer. I even almost confused myself there. So in other words, our arc length is going to be measured from the starting point, x naught, to x, of ds in terms of u. So what's that going to be? Well, it's going to be square root of 1 plus f prime of u squared du. And so now these are clearly u values, right? And so this is the arc length element, or sorry, the arc length function, as I wrote here, arc length function. It's the same as this, right? But this one is a little bit clearer to see how we're going to use it. Now for us on this problem, right, what do we know about x naught? Well, x naught is equal to 0, right? So x naught is equal to 0. And we've already computed pretty much everything else. We've got the hard part, right? So, and our ds in terms of u in this case is just secant of u du, right? We already did all that work, so we don't want to redo it, right? There was our ds. Now we just write ds in terms of u instead of just in terms of x. So we don't want to redo that. And so what we end up with then is this function, s of x, is equal to the integral from 0 to x of secant of u du, which we've already done a lot of the work, so I'm not going to redo it. We've done the antiderivative is log of secant u plus tangent u. The upper bound is going to become x now, right? The lower bound, 0, that one was 0, right? So that's gone as well. So I'm not going to redo this part of the work here of plugging in, but this becomes then, by all of our work from above, so I'll put 3 dots. So you should work this out. But if nothing else, go back and look at the work we just did. This becomes a natural log of secant of x plus tangent of x, all right? And that's it. So that's the arc length function. And this is only defined for x in this interval from negative pi over 2 to pi over 2. All right? Yeah, so there you go. So there's the arc length function for that curve, y equals, so this is, again, arc length function for y equals the natural log of secant of x. All right, there's the arclength function right there. So pretty cool, I think. I like that a lot. All right, here's one more, and then we'll call this video over. But this one says, let's say that we have a curve defined by x equals y to the 4th over 8 plus 1 over 4y squared. And this is going to be for y in the interval from 1 to 2. So in other words, the curve varies in the vertical direction from 1 to 2. So this one is given to us in a way that looks like we're going to want to write our ds in terms of y, right? So our ds in terms of y is going to be, remember, this is like our g of y. Now we've got a function. Our x is given to us as a function of y. Our g of y is going to be 1 plus g prime of y, quantity squared, dy. And so we need to carefully work this out, right? That's going to be the key. So let's do it. So our g of y, let's rewrite it in exactly the notation that we want to use right here. Our g of y is 1 over 8 y to the 4th plus 1/4 times y to the minus 2. I'm going to write it that way because we're going to have to take the derivative and then square it and do some stuff to it, right? So what happens? Well, now we've got g prime of y. What's that going to be? Well, we take the derivatives, right? So this becomes 1/2 y cubed plus, actually it's not, right? Minus 2. So minus 1/2 y to the minus 3 power. Okay, so just take the derivatives very carefully. You should get this. And now let's square this. So g prime of y, quantity squared, is going to be this whole thing, quantity squared. I'm going to really help us out here. 1/2 can come out, right? So 1/2 squared times y to the 3rd minus y to the minus 3rd. Let's see what happens. This becomes, like I said, the 1/2 just hangs out here. It becomes a 1/4 though. Let's square it. Let's actually square that. So 1/4. And then when we multiply this out, y, this is squared. I know you're yelling at me. There we go. That was squared. So this is then y to the 6th, right? Y cubed times y cubed, y to the 6th, minus 2 times y to the 0. I'll write it out, but think about what that is. And then plus y to the minus 6. All right, and let's go ahead and multiply through by this quarter now. So this is just g of y prime, right? So we now have a quarter, y to the 6, minus 2 over 4, so that's 1/2, y to the 0, that's just 1, right? So that's just 1/2 right there, minus 1/2. And then plus y 1/4, y to the minus 6. Remember, we have to add 1 to this, right? So what we just computed was this, right? G prime of y squared. We have to add 1 to it. So let's do that now. So 1 plus g prime of y, g prime of y squared is then 1 plus all of this, right? But since we have a constant term in the middle, we can add those up, right? So we've got 1 minus 1/2. Well, what's that going to become? Plus 1/2, right? And then let's reorder this. So this becomes 1/4 y to the 6 plus 1/2 plus 1/4 y to the minus 6. And then remember where this all came from. Let's factor out this quarter. Factor out this quarter and look what's left. Y to the 6th plus 2 plus y to the minus 6. And when you compare this with this one came from a perfect square, right? This one is going to as well, but what's going to change? That sign in the middle, right? So actually, this whole thing becomes then 1/2 quantity squared times y to the 3rd plus y to the minus 3rd quantity squared. And our ds is going to be, now this is where it's important, our y is positive, right? Our y is positive, so we don't have to worry about the square root and the squares and anything getting a sign that we don't want, right? Because this term will always be positive. So what we end up with then, and this is like the most work that we have had to do, and it will be the most work of this whole problem actually, our ds is the square root of this term, right? And notice I've got this all written in terms of squares of stuff that we know must be positive. So those are just going to cancel, right? So our halves cancel, our square root cancels, And our ds is equal to 1/2 times y cubed plus y to the minus 3 dy. So that's what we have to integrate, and we integrate on this interval from 1 to 2. You can probably do that on your own, but I'll do it because it's fun. So this is then the integral from 1 to 2 of ds, which again is the integral from, this is y equals 1 to 2. If you're going to write it like that, be very careful. Integral from 1 to 2 of 1/2 y cubed plus y to the minus 3 dy. So that's 1/2. And then when we integrate this, we end up with times 1/4 y to the 4th. Then we get what? Minus 1/4 y to the minus 2. And we plug in y equals 1 and 2. All right, it's a beautiful thing. So this is 1/2 times, this is going to be what? 1/4 times 16. So that's going to be 4. I'll just do these in order, I guess. So 4 minus this is going to be 1/4 times 1/4, so another 16th. And then we're going to have a minus 1/4 plus 1/4 here. You better check this. And what do we end up with? These cancel. This is going to be what? 64/4, so 63. This will end up being 63 over 32. So 63 30-seconds. You better check this. All right, but I'm going to assume that it's right. If it's wrong, you'll fix it. And either way, we'll be smiling. That is the arc length of this curve that we were given. All right, guys, I hope this helps you out, and I'll see you guys in the next lecture.